Okay, so let's continue. And what I was talking before was about really abstract representation theory. It's just superconformal algebra or superconformal group. And in principle, it has nothing to do with the field theory. Now, what we would like to do, we would like to talk about the concrete n equals 4 super Young-Mills. And we would like to understand, for instance, what is the spectrum of these primary fields in n equals 4. And since n equals 4 super Young-Mills is a conformal field theory, as you probably have heard, in order to solve the conformal field theory, what you have to find is a spectrum of primary fields, spectrum of primary operators. And the second thing is 3-point correlation functions of these primary fields. And then, due to the convergence of OPE, operator product expansion in Euclidean theory, you can build up any correlation function out of this knowledge. Spectrum of primary fields plus 3-point correlation functions. And so the first task is, of course, to understand what is the spectrum of primary fields. And primary field, every primary field is a highest weight state of the superconformal algebra. And as such, it's characterized by a set of Dynkin labels. And among of these Dynkin labels, there is one which is in general continuous and which depends on the coupling constant of the theory. And this Dynkin label is the dilatation weight, delta. So the task now consists in finding the spectrum of n equals 4, which means finding primary fields and the dimension and their dimensions delta. And a priori this is a very complicated task because what we deal here is a 4-dimensional quantum field theory, and the methods which we knew before the discovery of integrability was the standard methods of quantum field theory, which are very extremely important methods based on perturbation theory, namely computation of certain quantities, like for instance dimension of operators, by means of perturbation theory, loop by loop order. And you will hear a lot about these kind of computations during this school. You will study these higher loop techniques, for instance, how people do it in modern computations, in modern language, how people do very complicated computations of this kind. Now, concerning n equals 4, therefore, what I would like first to do is to consider the question about primary operators, what they are. What kind of operators I can consider in this theory. And the most natural assumption, most natural approach is to consider composite fields. So composite fields, these are fields which are built up from elementary fields of n equals 4 theory. That means from 6 scalars, gauge field mu, covariant derivative, and so on, in such a way that these composite fields are the products of elementary fields taken in the one and the same space-time point. And these products must be gauge invariant, because gauge invariant quantities are the only observable quantities in this theory. So a typical example of such an operator, for instance, could be given by the product of scalar fields taken at the one and the same space-time point. Now, such fields in classical theory, where you put coupling constant to 0, so there is no interaction. Classically, such fields all have a very well-defined conformal dimension, which is simply given by sum of the dimensions of elementary fields. For instance, scalar field has dimension 1. And if you have n such a field, the dimension of such an operator would be simply n. But the realm of quantum field theory tells that in the quantum field theory, actually, such composite operators undergo renormalization. And as a result, their classical dimension gets shifted by an anomalous amount. In other words, these fields acquire anomalous dimension. An anomalous dimension becomes a function of the coupling constant of this theory. Moreover, it appears that if you start from two fields in the classical theory, and you make these fields orthogonal at the classical level, which means that the two-point function, which you compute by just taking elementary weak contractions between the fields, actually these two fields orthogonal at the classical level might not keep their orthogonality at the quantum level. Because of the quantum correction, they can acquire a non-trivial contribution to their two-point function. And orthogonality can be spoiled precisely by taking into account these quantum corrections. And that means that if you orthogonalized fields as a classical level, at the quantum level they might not become orthogonal, and you have to redefine your fields again in order to achieve orthogonality, say at one loop, and then again at two loops, at three loops, and so on. So that means that you have to change constantly the basis of fields at any given loop order in order to keep orthogonality of the fields. This is, of course, related to the phenomenon of renormalization, and it consists in the following. So if you start from the bare field, which looks like precisely like a classical field, it is a classical field, then if you compute, say, the two-point function of such bare fields, you will discover that this two-point function might not exist because of the divergence of the corresponding Feynman integral. So you need to perform renormalization program. And renormalization program typically is what typically arises, a phenomenon which arises, namely what you need to do mixing. That means that fields which have the same classical dimension and the same group theoretic content in perturbation theory can mix with each other. That means that first they were orthogonal, say at tree level. At one loop they are not orthogonal. But if you change the basis of these fields by means of what is called mixing matrix, so you perform rotation on this bare fields, you can achieve first of all a new basis, which I call the basis of renormalized fields. And if you make this mixing matrix Z to be dependent on the cutoff in such a way that when you compute the two-point function for the renormalized fields and you pick up the cutoff dependence in Z in such a way that when you remove the cutoff, the two-point correlation function becomes finite, then what you achieved is you achieved the finite two-point function, and you achieve this by means of two things. You mix your fields and you make the mixing matrix. You pick up a special dependence of the mixing matrix on the cutoff in such a way that when you remove the cutoff, you get a finite two-point correlation function. So this is basically the idea of renormalization. In the simplest situation, when we have just one scalar field, mixing is not needed. Mixing is not needed, and renormalization, which you consider here, is what is called wave function renormalization, where you renormalize wave function of the field. You make a wave function prefactor to be dependent on the scale. Yeah, you have a question.
Might be naive, but what does this mixing matrix V now have to do with the dilatation operator we find of our field?
Mixing matrix, so basically, operators at the tree level, they are eigenstates of the dilatation operator because they have well-defined conformal dimensions. Conformal dimension is simply given by the sum of classical dimensions. Right? So these fields have a well-defined conformal dimension. Now, when you consider the perturbation theory, mixing matrix does appear because you need to mix the field in order to achieve a renormalized, that means finite correlation functions. You need to mix the field and you need to keep orthogonality. Because orthogonality of the two fields in conformal field theory, if you achieve, say, for two fields, say for x or y, correlation function of two primary fields, or let's take it normalized to 1, it has a full x minus y in the power 2 delta, where delta is precisely the same thing as dilatation width of conformal dimension. This conformal dimension. This is basically the form of two-point correlation function which is dictated by conformal symmetry. Now, when you diagonalize the mixing matrix, that means that you come to the new basis of fields, where the two-point function of these fields becomes diagonal. And these fields, it means automatically that these fields has very well defined the notion of the dilatation weight. They have a definite conformal dimension. So before you perform this diagonalization of the matrix, you don't know what is the conformal dimension of your fields. And your fields are not primary fields. When you diagonalize it, now these fields acquire a well-defined anomalous dimension. And from this point of view, they are eigenstates of the dilatation operator because their dimension is well-defined. So in other words, to find the dilatation operator, what you need to do, you need to find the mixing matrix and diagonalize it. Then the individual eigenvalues are conformal dimension of the fields, which participate in this mixing. So that is precisely what I said. So dilatation defines the mixing matrix, and the individual eigenstates of this mixing matrix are precisely primary operators. Well, of course, this is not so easy as I am telling you there, because of course, in order for this operator to be primary, you have to verify that it's annihilated by the generator of special conformal symmetry also. This is quite non-trivial, by the way. Okay? It's not on this transparency, but I'm telling you that to find out that the operator is primary in quantum field theory is not an easy exercise. It's not always an easy exercise. Because you somehow have to understand that this operator is a highest weight state also. So it's annihilated by the generator of the conformal symmetry. And of course, then it also needs to be eigenstate of the dilatation operator with a definite dilatation weight, which you find through this mixing matrix. Now, let's concentrate now on n equals 4 theory. And as I told you, in this theory, we have two coupling constants. So the dilatation, the eigenvalues of the dilatation operator will be functions of these constants. Coupling constant and the rank of the gauge group, and typically instead of m and g squared, one introduces the 't Hooft coupling lambda, which is a product g squared by n, and 1 over n. And 't Hooft suggested to consider a special limit of this theory where the theory becomes much more tractable, namely the limit when n's tend to infinity. This is called Lagrangian limit. Because in this limit, only a special type of graphs contributes, so-called planar graphs. And in other words, this limit is called planar limit. And this is in this limit, planar limit, what we would like to study this n equals 4 theory. Simplified limit, where certain subclass, only certain subclass of Feynman diagrams survive. Okay, so now let's come to interpretation of such composite operators in terms of spin chain. Yeah?
Second question, is there any reason why I don't have multiple traces? Would that still not be a local gauge operator?
No, they will be. Why not? You can have multiple traces, absolutely. That's here I have just one trace, so it's a single trace operator. Gauge invariant operators, of course, if I have one, I can take products of them and so on. But from the point of view of 1 over n expansion, the single trace operators are the operators which survive, which constitute the spectrum. Modulo certain subtleties which I don't want to go in now. Modulo these assumptions, single traces are most important operators in the Lagrangian limit. Of course, if you go beyond 1 over n, you have to take into account also operators which are not single traces. That is true. Yeah. Thank you for your question. Yeah. So now, what we can do, we can change completely change the view on the composite operator and completely forget about the point x, space-time point, which is present in this operator. We can completely forget about it. And for this simplest single trace operator made of scalar fields, you can build up a representation for this operator in terms of a state of a closed spin chain. So since we have 6 scalars, index I1, I2, each of these indices, I1, I2, and so on, IL, can run 6 possible values. So you can have 6 possible polarizations. And you represent any of these fields as a state which sits on a side of a closed chain. And in any of these sites, you can think about this as a field as being an arrow which can point in one of the possible 6 directions. So field has 6 polarizations. And closeness, why it is closed, that is because we put these fields under the trace. So you can say that such a state, or such an operator, is equivalent to a state of a spin chain. So if you pick up indices I1, I2, and so on, IL to some concrete values, you get one state of this chain. If you change this I1, I2, and so on, IL, you get another state. So you get different states of this spin chain. So at each position you can have 6 states, and another you have another 6, and so on. So in general you have many states, like 6 in the power n, right? 6 in the power n states. 6 by 6 by 6 by 6 by 6, and so on. Okay, now what you can do, you can compute explicitly the mixing matrix at one loop. For instance, start doing this evaluation of the mixing matrix at one loop in the hope to find individual eigenvalues of the dilatation operator, the same as eigenvalues of the mixing matrix, say at one loop level. Okay? And the statement is that by n equals 4 Lagrangian, at one loop, these fields, which are excitations of this spin chain, they mix. That essentially means that this matrix, which acts at one loop on this state of the spin chain, is not diagonal. So the dilatation matrix is not diagonal, so it transforms one state into the other state. And the mixing matrix is just a matrix which you apply to a set of fields in a certain, and sum over all possible polarizations. So ZA, ZB, ZC are 3 mixing matrices, which I represent here, and they correspond to 3 one-loop graphs, which you will have in n equals 4 theory. So at one-loop graphs, you have the possibility of exchange by gauge boson. This is a graph number 1. So these lines which go from K and L positions up, they represent scalar fields. And these scalar fields can exchange by gauge boson according to this Lagrangian of n equals 4 theory, or they can have a quartic interaction, which correspond to this quartic commutated term in the Lagrangian, or there is also contribution to the self-energy contribution for a scalar field. So you have 3 graphs. These individual 3 graphs are divergent. And that you see in the mixing matrix by the presence of the logarithmic scale. Lambda is a cutoff, and you have a logarithm lambda. Okay? So this is an explicit form, explicit computation of the mixing matrix. Any questions? If you understand how it works? Well, yeah?
I'm a bit confused on how these diagrams relate to the traces.
What you do, you forget about the trace. Forget about the trace. So you have fields. Every field is a state of a chain, right? Now, what you do, you take, you bring to this chain of excitations, you bring close another chain, and in between these two, you substitute the Young-Mills Lagrangian, and then you perform weak contractions. So possible weak contractions with legs which go from the interaction vertex into your operator, into the state of a spin chain in and up. And the mixing matrix is something which you obtain by cutting off this by half. So you see the result of application of interaction into the state, and then you produce another state. So that's why you get indices of the mixing matrix which act on a state. This is a low indices, and you get indices up which you obtain when you act. So this is a big matrix. So this matrix should be applied to a state here. So number of these fields is precisely the number of indices in the mixing matrix.
So diagram C is a different case, which is only one index?
Sorry?
Diagram C describes different cases than A and B, because there's only one index?
No, this is particular, I'm zooming on a particular indices, K and L. And L actually is equal to K plus 1.
Right.
Then there will be another indices and so on and so on. That's why you see that this Z, ZA, ZB, ZC, they have many indices. They have many indices, but once you have an insertion of interaction for K and K plus 1, you get the right-hand side corresponding to this concrete graph. And then the whole mixing matrix is obtained by summing up these three. So this is how it looks like. And in the following, it's convenient, well, when you look at this structure of Kroneker's, you will see that one of these products, namely, I think the first one should be identified with a permutation operator. And the other one is another operator, which is called K, and it's called a trace operator. So basically, what is written down on the first line can be summarized in the formula, which I denote as a D1 loop. D1 loop is a dilatation matrix, a mixing matrix, so the same as a dilatation operator in one loop. And it's given by the second term, which is identity. You see IK, JK, IK plus 1 goes to JK plus 1. This term corresponds to identity. Then the next one is the first term on the first line. It corresponds to permutation. And the last term, it corresponds to the taken trace. So this is a structure of this mixing matrix. It contains identity. It contains a permutation of neighbor excitations on the neighboring sites, site I and I plus 1, and it contains what is called K, what is trace. And then an important observation is that looking at this dilatation operator as an operator acting on the states of the spin chain, which I presented before, this dilatation operator should be identified or can be identified, or if you wish, nothing else, as the Hamiltonian of the so-called integrable SO6 spin chain. Okay, so this is an important observation. So dilatation operator appears to be the same as the Hamiltonian of SO6 integrable spin chain. Now you can, if you wish, you can simplify the picture where you get even more intuition and more insight from the spin chain picture. You can reduce the theory in a sense that you can consider not generic operators with SO6 indices, like I presented here, but even simpler operators made of two complex scalars of n equals 4. So basically you take just Z1 and Z2 and you forget about other two scalars. And you consider operators, you call this field Z and W, and you consider operators of this type made of W and Z. And this W and Z, they can have different positions under the trace. So W can mix with Z. This is signified by putting here plus dot, 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 dot. So you can have many operators where W is distributed among Z in different ways. This is, from the point of view of what we have just saw, can be represented by even simpler spin chains, where you say identify field Z with an excitation corresponding to spin up, and field W with the excitation corresponding to spin down. spin ups and spin down. And then the Hamiltonian actually for this spin chain is obtained from the previous one by reduction, namely by throwing away trace k. Trace k does not contribute for this smaller reduced spin chain. And the Hamiltonian which arises in this case is a Hamiltonian of the famous Heisenberg XXX spin chain, which is known to be integrable. And integrability, so this is a quantum spin chain, it's not classical one. And integrability means that in addition to the Hamiltonian, there is a set of commuting operators, commuting charges, which commute between themselves and which commute with the Hamiltonian. And all of this, therefore, can be simultaneously diagonalized. Now, these higher charges, which makes this model integrable, I'm not writing here, so I'm just tell you this, please take it as a statement that this spin chain is integrable. Now, it appears that n equals 4 superentials there are other sectors for which are closed under normalization, not even at one loop, but also at high loops. It means that if you restrict your attention to the operators from this small sector, then you don't need any other operators, because these operators from a small sector, they do not mix under normalization. They don't need any other operators. They always stay orthogonal with anything else. And these sectors I represented for you sectors of rank 1. The first one, SU2. This is operators we have just discussed. Then there is a very important SL2 sector, to which I will be turning my attention later on. This is made of covariant derivatives in the field Z. So just one scalar, complex scalar Z in certain power J, and covariant derivatives. Covariant derivative which is participating there is a so-called light cone covariant derivative made of D1 and say and D2. Dots mean that you can put the derivative at various positions between these. There is a so-called SU1/1 sector which involves complex scalar Z in the fermion psi, one fermion. And there are other sectors, but the biggest one, which is closed under normalization, is known to be the so-called SU2/3. It consists of 3 complex scalars and 2 complex fermions. Okay? So when you will be looking at the literature, you will often find these statements about various sectors, and the most popular ones which people study a lot is SU2 and SL2. But sometimes also important things are done with SU1/1 and so on. Good. Now, what is important? Even if you don't restrict your attention to a particular sector, a particular operator, and consider the whole family of all possible gauge invariant operators you can write down, the statement is that you can treat this set of operators as excitations of the so-called PSU2,2/4 integrable spin chain. So SO6 in my original discussion is isomorphic to SU4, and this is a SO6 spin chain, but SO6 is a subgroup of PSU2,2/4. So in general, if you allow all possible excitations, then the spin chain which you get is precisely the superconformal group. So it means that these polarizations which can sit at a site takes excitations of PSU2,2/4. Okay, so it's such a spin chain, and it's rather complicated because it's a non-compact algebra. So it's quite complicated. Now, the fact that it's integrable at one loop means that it can be solved by means of beta ansatz. Beta ansatz is something which I will be talking later. So let me just say at this point that at one loop, this is PSU2,2/4 integrable spin chain, and we know how to find the spectrum of the dilatation operator It means that we know the dimensions, we know the conformal dimensions of all primary fields. We can build up out of this composite operators. At this point, you start to wonder, but what happens at higher loops? What happens at higher loops? And you can restrict your attention, since I told you that this is, say, for instance, if you look up at the SU2 sector, you can, since operators from this sector do not mix with anything else, you can look at what happens with a dilatation operator, say at 2 and 3 loops in the SU2 sector, how the dilatation operator changes. Now, the characteristic feature of the XXX Heisenberg Hamiltonian, which is the same as the dilatation operator of one loop, is that this permutation involves only nearest neighboring excitations, excitations sitting at site I and I plus 1. So these excitations by the permutation operator, they just permuted. But they are nearest neighboring interactions. When you go to the next loop level, it appears that you cannot stay with just with identity and with this simple permutation operator. The Hamiltonian gets deformed and gets more complicated terms, which involve now interaction between 3 neighboring spins. So between spin and its 2 nearest neighbors. So it means, in fact, that you are talking about now, you are talking about 3-body interaction. So 3 bodies are involved. One loop, 2 bodies are involved. Next next loop level, 3 bodies are involved, and of course you anticipate that at 3 loops, 4 bodies are involved, and so on. So that means that dilatation operator now gets modified at higher loops, and you can still show that integrability is preserved in a perturbative sense, and dilatation operator continues to act as an integrable Hamiltonian of a long-range spin chain. So explicitly, I gave for you how these Hamiltonians look like. So say at 1 loop you get the Heisenberg Hamiltonian, and 2 loops you see you get permutation, and then you get this guy which permutes I and I plus 2 excitations, sitting at I and I plus 2. At 3 loops, you get more complicated things, even products of such permutations appear, and so on. And so the complexity of these Hamiltonians increases. When you go to high and higher loops, the complexity increases. And of course, at a certain point, you ask yourself the following question. So suppose your operator involves a finite number of fields, right? So finite number of fields. You increase now the loop order. So first you get 2-body interaction, 3-body interaction, so on. So interaction spreads over the operator. It becomes more and more and more and more and more local. And what happens at the end? It becomes so non-local that it wraps around. It starts wrapping around your operator. And at this point, the form of the Hamiltonian becomes non-universal. The form does not depend anymore on the length, just through the integration bound, just through the summation bound. You see here the dependence on how many fields, what is the length of this spin chain, is rendered by this summation bound L. But when you go to higher and higher loops, at a certain point, this interaction has start to have a dependence on L, not only through the bound, but also it becomes non-universal. It starts to depend to which length operator is applied. Okay? So at this point, interpretation of the dilatation operator as a Hamiltonian of integrable long-range spin chain is lost. And to my knowledge, up to now, we don't have any satisfactory answer how to treat this problem of wrapping around. And so at this point, to my mind, interpretation in terms of long-range spin chains cease to work. And this is a point where you have to resort to the description coming from strings on alias 5 crosses 5. this is, at this point, our understanding of how to proceed at higher loops is not anymore there. Okay? Good. And this is where I naturally stop with the discussing the integrable structure of the quantum field theory. So if you would like to ask me some questions here at this point, please go ahead. Yeah?
This mixing
Mm-hmm.
is it hard to compute? I mean,
No, you can compute it, no problem. It just becomes non-universal. It starts to depend, really to depend to which operator it's applied. It depends not only through, you cannot represent it in this simple form as a universal sum, where L dependence is only in this sum. You can compute it. You can go. There's nothing wrong with field theory.
so one computer observes that this coincides with the Hamiltonian.
Right. You compute and you see, wow, it is my spin chain and which is integrable. Then you go to next loop, and then you are in trouble because at a certain point, this picture is not anymore there.
And does this depend on the regularization procedure, randomization procedure or not?
No, this does not depend on renormalization procedure. No. In n equals 4 theory, scaling dimensions is a quantity. A scaling dimension is a quantity which has an absolute meaning because beta function is equal to 0. Okay. So in n equals 4, it makes sense to compute anomalous dimension at any loop order. It does not depend on anything. Good. Any other questions? Yeah?
Where does appear the renormalization scale lambda?
Scale lambda is factor out when you basically you see you divide by this dz over d log z, and then you take z minus 1. So basically it disappeared. It's not there. It's not there.
But maybe the question is that it really is the divergence of the graphs that you drew, right?
Yes, of course.
Yes, so maybe,
Sure.
Maybe
Yeah.
you're going to go to the slide that you have the graphs.
Yes, let's go to the slide where we have graphs.
So this is important.
Sure.
Indeed, maybe just to clarify, yes, the indices K and L really correspond to different fields on the trace. And you do the usual perturbation theory, we see they are one-loop graphs, okay? You do have a loop. These fields inside your trace exchange other fields, and so one computes those graphs and they are divergent. And this is the log lambda that we also asked about.
So basically at one loop everything is simple. It's seen from here. When you will be differentiating with respect to log lambda disappeared, right? But then you need to multiply this by z minus 1 matrix. But this derivative of dz is already of order lambda because 1 is gone away after differentiation over d log z. And therefore from z minus 1, at one loop, you have to take just one, the first term in perturbation theory. And that's why log lambda just disappeared. You see, you differentiate over it and it goes away. So at one loop, it's easy to see it. You can show it immediately on this example. Okay. No, but by itself, it's a very interesting problem, how to actually not to rely on string theory and somehow to understand this how to say intrinsic string theoretic structure, which we observe by looking at string from the field theoretic point of view, what trapping means actually. That is an open problem. I mean, to my knowledge, we don't have any very good description. Yeah?
Can you construct some operators with as anomalous beta dimension that doesn't renormalize? You should the anomalous dimension is equal to the classical one.
Sorry, you?
Can you
Yeah.
construct some operators, some trace operators, some operators that has the anomalous dimension equal to 0? We are sure that the
Yes, there are operators, yes. There are operators which do not acquire anomalous dimension at all. These are, for instance, 1/2 BPS operators. As you have seen from my classification of unitary representations, where was it? It was somewhere here. Yes, here. You see that, say, for instance, for operators of series C, dimension is exactly given in terms of Dynkin labels. Dynkin labels are integers, as you fall. It means they cannot depend on the Kaufman constant, right? And since they cannot depend on the Kaufman constant, that means the dimension should stay untouched. It cannot change in perturbation theory. It remains one and the same. So these operators are not renormalized, they stay the same. But for instance, operators from series A, for them, unitarity means only the bound. And so in principle, dimension can change. It can grow, for example, beyond the bound. And this is those operators which do receive quantum corrections and for which dimension becomes a function of the Kaufman constant. That is true. Okay. Yeah, probably you wanted also to ask what happens if you apply the dilatation operator to operators which do not acquire anomalous dimension. Nothing. Their dimension is simply stays classical. This correction disappears. They just annihilated by higher loop dilatation operators. They just annihilated. But this information is not enough. Information on the protected sector, on the sector which is protected under quantum corrections, is not enough. By no means, it's not enough to reconstruct the form of the dilatation operator as higher loops. People tried, but it's not enough information. You understand what I'm trying to say? No. Okay, maybe, yeah, it maybe become more clear. Good. So we resort now to the discussion of string theory. So this is a part 3, and as I promised, this will be the biggest part. And I think this is a part where these integrability methods made the most spectacular progress, considering string theory. And so I start from the sigma model description, which essentially, well, the way to describe now strings propagating in this ADS5 cross S5 space-time. So may I ask you, who had a course on string theory? Can you raise your hands? Well, there's quite enough people, so I don't need to tell you what string theory is. That is very good. Okay. Okay, so string, one-dimensional object. And now I take this string and throw it away in the ADS5 cross S5, and it propagates somehow there. And what is the ADS5 cross S5 superstring? So first I need to describe what is ADS5 cross S5. If you look at the ADS5 cross S5, you can realize that this space is a coset, where you start from the group SO4,2 cross SO6, and you divide SO4,2 by SO4,1, and SO6 you divide by SO5. SO6 by SO5, it's a 5 sphere. And SO4,2 by SO4,1 is ADS5 space. And so what people consider, they consider the model to describe strings propagated in ADS5 cross S5, where they take as a target space in which string propagates the supercoset, where in the numerator you see this PSU 2,2/4 superconformal group, and you put in the denominator of the coset precisely the bosonic subgroup SO4,1 cross SO5, And therefore, if you just restrict your attention to the bosonic subgroup of the numerator, then the bosonic part of this coset is precisely ADS5 process 5 space. And the rest, what is in PSU, 2/4, is described by fermionic degrees of freedom. So that is precisely what makes this fermionic degrees of freedom of the superstring. So SO 4,2 cross SO6 is a maximal bosonic subgroup which sits in PSU 2,2/3. And factoring this out by this denominator, we obtain the ADS5 process 5 space. Good. Now, yeah.
I'm not sure that many people have been introduced to the ADS-CFT correspondence, so hopefully this will be part of your lectures at some point. Before discussing the ADS-5 cross-function with one, or at least at some point make a connection to the gauge theory you just described.
Yes. So okay. Right. Yeah. Very briefly. So. Yeah. So I continue to talk about the gauge theory, which is N equals 4 super Young-Mills. And by this holographic duality, this theory is supposed to be equivalent to string theory, strings on ADS 5 cross S5. Now, of course, a priori, when you look at this, you extremely surprised. This is two very, very different theories. First of all, this lives in 10 dimensions, and this is a gauge theory. This lives in 4 dimensions, and this is a gauge theory. Gauge theory, which I described by means of that Lagrangian. Now, string theory and ADS5, they propagate on the 10-dimensional manifold. So these are one-dimensional strings, and these are closed strings. So this is the theory of closed strings. Strings with a topology of a circle, and they propagate on this 10-dimensional manifold. So ADS5, it's anti-de Sitter space, 5-dimensional. This is a space of, this is maximally symmetric space of constant negative curvature. Looks like this. And S5 is a 5-sphere. A 5-sphere you can imagine, right? Yes, it's a little bit more difficult, but okay. This is, I draw a picture for you. Now, two completely different descriptions, and somehow, they still suppose to be completely equivalent. And from the point of view of what is exactly equivalent to what, in my case, well, I will formulate it in a very opposite pedestrian language. I can just say that the quantity which I'm interested here, N equals 4, which I'm computing, is a spectrum of primary operators. Those one which we just discussed. And those primary operators are, okay, so let's write here. Let it be gauge theory, let's say primary operators. Primary operators. And primary operators are characterized, in particular, by the spectrum of anomalous or scaling dimensions in general, scaling dimensions, depending on the Kaufman constant. And the Kaufman constant, say with the Latin limit, there is only one Kaufman, and this is a 12 Kaufman. So dimensions as a functions of 12 Kaufman, dimensions of primary operators, this is what I'm interested in. They constitute the spectrum of this. On the other hand, when I consider string theory, here I have to talk about string spectrum, or spectrum of string states. Spectrum of string states. And in particular, I have to talk about spectrum means energy levels of the string states. So there is an energy, there is a notion of the energy. And by this holographic correspondence, spectrum of string states, or string theory in ADS5 process 5, also has a Kaufman constant. And this constant is a string tension. String tension is a function of lambda. So at the end of the day, these energies are also a function of lambda. And the correspondence should establish a one-to-one equivalence between spectrum of string states and spectrum of primary operators, where, of course, dimensions should match the energies of the states. Okay? It's a conjecture of Maldacena that it should be the case, and all our integrability methods, which we are developing both on gauge theory side and on the string theory side, are supposed to provide evidence in favor of this conjecture. Okay? This is in simple terms, without going into too much details. Okay, now can I go further?
Let's see if the students have any more questions or would like to elaborate more.
Yeah, of course I'm omitting why Maldacena came to this conjecture. That is something which I'm not telling you why, but yeah, you can look at the original paper and find out why. By the way, people suspected that n equals 4 theory is a special theory which should be integrable in one and in that sense since very early days of its discovery. I think Witten suggested that it must be integrable.
Witten, you said?
Yes. He has a paper on dionic states where he says that it's quite probable that this theory is integrable, but in which sense, of course, it was not very much clear. Because it has an electromagnetic duality. This is another very interesting and intriguing property which this theory possesses, electromagnetic duality. And that basically, from this point of view, he made the statement that probably this theory must be integrable in that sense. But now, at least in the Lagrangian limit, we see the sense in which this theory is integrable. We can find the spectrum of primary operators by using integrability methods. Although, according to what I told you today, we can do it today from string theory, not fully, logically fully from the point of view of the gauge theory, because of this wrapping problem. Okay. So I would like to describe what is this string on ADS5 cross S5. But for that I need to tell you a little bit about how the Lagrangian for this string theory is constructed. When you get the course on usual string theory, string theory in the flat space, people showed you how Lagrangian look like, right? You talk about Polyakov Lagrangian or Polyakov action. Right? That is, or Nambu-Goto action. But I would like to construct something similar here. I would like first to represent to you what is a dynamical system which is a string on ADS5 cross S5 space. Of course, it's more complicated than string in the flat space. String in the flat space is essentially free, can be elementary solved. You do it in your string course. Now, when background becomes curved, this theory becomes rather complicated because it is nonlinear theory, and to find a spectrum becomes a problem. Easy in flat space, difficult in ADS5 cross S5. Because of the curvature of the space, the theory is sort of self-interacting, and to solve it, you have to develop special methods. And this is what I will be doing till the end of my mission. Good. So let's return back a little bit to the discussion of super Lie algebras. Now I would like to repeat what I told you before about 8x8 matrices, but now at a little bit different level and more, how to say, quietly and in a more relaxed manner. In a more relaxed manner, we define SL4/4 as an algebra of 8x8 matrices. So I represent this matrix in terms of 4x4 blocks. So SL4/4 is defined by the requirement that its supertrace is equal to 0. And supertrace is a trace of the block 4x4 block M minus trace of 4x4 block n. That is what is called supertrace, and supertrace is required to be 0. Now, I will describe this space of 8x8 matrices, which constitute SL 4/4, in terms of what is called Grassmann envelope. So the blocks M and N are considered as made of bosonic variables. It means usual numbers. While the off-diagonal blocks, which are represented here by zeta and eta, they are supposed to be 4x4 blocks made of fermions, anti-commuting or Grassmann variables. Now, the compact form SU2,2/4 is distinguished by imposition of a certain reality condition. And this reality condition is written down here. So m dega h plus hm is equal to 0, where h is a certain matrix. Well, it has, it's a 8x8 matrix, which has one block here, diagonal block, which has 1, 1, minus 1, minus 1, and here all blocks. Okay? So this is related to signature of SU2, signature of conformal group, and this is related to SU4. So if you now write this reality condition for individual blocks, you will see that for the upper diagonal block M, it reduces to usual conditions that you have the group U2, 2. N dega is equal to minus n. Of course, it defines for you the Lie algebra U4. No, and fermions are related. Eta dega is obtained from zeta by multiplication with this matrix sigma. Good. This shows that, in fact, the bosonic subalgebra of SU2,2/4 is made of SU2, SU4, and there is one extra U1 generator. U1 generator, which is identity multiplied by I. Identity multiplied by I, it satisfies this reality condition. Agree? Identity commutes with H because it's identity matrix. And I dega plus I is equal to 0 because it's I. So the generator I1 satisfies reality condition, and it has vanishing supertrace. Identity has vanishing supertrace. So I identity is a generator which belongs SU2,2/4. So the full bosonic subalgebra is therefore SU2,2 plus SU4 plus U1. And there was a question about letter P. Yeah? You asked me what is P in PSU2,2/4. So PSU2,2/4 is defined in strict mathematical terms as a factor algebra of SU2,2/4 over this U1 generated by I multiplied by identity. Over this U1. Now, why you cannot just say that you consider traceless matrices? Because traceless matrices, in addition to the fact that it has a vanishing supertrace, you can say that you consider traceless matrices. Why you need to take this factor? The factor you need to take because of fermions. Because even if you consider traceless matrices without identity, then when you compute the commutator of Grassmann, of matrices which involve Grassmann variables, then the commutator for Grassmann variables will transform into anti-commutator, and the anti-commutator will generate on the right-hand side identity. So identity will be generated because of fermions, because of this extra block, so it will be generated back. So even if you start from matrices which have no identity on the diagonal, but which have fermionic blocks, upon commutation of such a matrices, this identity appear back as a result of commuting fermions. So what you need to do, you start to work in with traceless matrices, but you will generate them anti-commutators, So in order to get rid of them, you say that now you just don't care about them, which means that you go to the vector space. And this is what this PSU2,2/4 is supposed to be. Okay. Now, this algebra has an external automorphism called supertransposition. So matrix M goes to minus M supertransposed. And supertransposition is defined here, so this is the definition. You basically transpose the matrix, but on the top of that you put extra minus in front of eta. And so when you transpose another time, so supertranspose twice, you don't return back. Usual transposition you return back, but for supertransposition you don't. So supertransposition square does not return you back, and it's clear that you need to transpose 2 more times in order to return back, to restore the signs. So when you transpose matrix supertranspose 4 times, you return back. And basically this external automorphism, which is this supertransposition, allows to decompose your Lie superalgebra, which is in our case PSU2,2/4, into the sum of graded spaces. Every space in this decomposition is an eigenstate of this external automorphism with an eigenvalue being equal to 4th root of unity. Right? These are powers of 4th root of unity. So graded decomposition means precisely that the commutator of elements from the space Jk and Jm produce your element which lives in the space Jk plus m. Now imagine that we have an element of the group SU2,2/4. What we can do? We can define a current, G minus 1 dg. I call this current A. And then this current takes value, of course, in the Lie algebra, SU2,2/4. And therefore, we can decompose this element into the sum of graded components, A0, A1, A2, plus A3. So components A0 and A2, they are bosonic, and A3 and A4, they are fermionic. So they even and odd. 0 and 2 are even, and 1 and 3 are odd. Now this current constructed as G minus 1 dg, it has zero curvature. G minus 1g is called Maurer-Cartan form, and its differential produce for you an equation that dA is equal to A wedge A. But this follows just from the definition. If you just apply external differential to A, you will obtain this equation. And this equation, if you write it in components, it's precisely what I'm writing there as d alpha A beta minus d beta alpha minus commutator alpha beta is equal to 0. And then the Lagrangian for strings on ADS5 cross S5 is given by this formula here. So you take graded component 2 and another 2 and multiply it with gamma alpha beta, where gamma alpha beta is a invariant standard combination of the worldsheet metric. So worldsheet metric is H alpha beta, and H is a determinant of H alpha beta. So this term is a kinetic one. This is a kinetic term. It depends on the worldsheet metric. And in addition to this kinetic term, there is another term which is called Wess-Zumina term. It does not depend on the worldsheet metric. It's a topological term in the sense that it does not depend on the worldsheet metric. It involves only two-dimensional tensor epsilon alpha beta. And there is a parameter kappa here which can take two values, either +1 or -1. For a certain reason I will tell you in a second. So this is an explicit Lagrangian. An explicit Lagrangian we would like to use to talk about, this is Lagrangian for string theory in ADS5 process. G is a string tension. Well, it's slightly modified string tension because when I put my string theory in ADS5 process 5, ADS5 and this is 5-dimensional sphere, they have a radius 1. inside, because I take an arbitrary radius r and rescale my fields in such a way that this radius gets out as an overall coupling constant, r squared. And it then combines with a standard 1/2 pi alpha prime, which you put in front of the polar convection. And together they produce an effective coupling, which I call G. Any questions? Is this construction clear?
How is your G compared to the tooth coupling?
Yes. So throughout this presentation, G will be related to the Hopf coupling by this formula. G is equal to square root of lambda over 2 pi. This is what will be throughout this presentation. Or E squared, sometimes I will use this. Good.
But then I think Gleb,
Yeah. Mm-hmm.
you should have. Yes, very good. Indeed, yes, there should be square root of lambda in front of the axis. That's what I was just having.
Yes. Okay. Yeah.
So before this duality was discovered, why were people looking at especially strings and this thing, this ADS5, S5? Why not ADS? Like, did they just interested in all sorts of geometries, or is there something interesting about this?
There are various ways how you can explain this. One of the arguments, well, there are certain physical arguments. There is also a very clean mathematical argument. You know that n equals 4 theory is invariant with respect to PSU 2,2/4. So PSU 2,2/4, or simply let's consider just its conformal part, say SO4,2 is a conformal group under which n equals 4 theory is invariant. So it's a symmetry. SO4,2 is a symmetry. On the other hand, for ADS5, SO4,2 is an isometry of this background. So if it's an isometry of this background, it means that this is a global symmetry of the string theory, which we are discussing. And that's what I was going to tell you in a second. I'm going to tell you in a second, okay? So a conformal group in 4 dimensions is the same as the isometry group of the ADS5 space. Internal symmetry group of n equals 4 theory is SU4. And SU4 is SO6. And SO6 is a global symmetry group of the 5 sphere. It means a global symmetry group of this string theory on ADS5 cross S5. That means that from the kinematical point of view, we have 2 very different theories, but they possess the one and the same global symmetries. It does not really tell you that this theory must be the one and the same. It's a question about kinematics. But at least kinematical agreement is there. Both theories have the one and the same kinematical symmetry group. And in general, the whole symmetry group is PSU 2,2/4 in Young-Mills and also on the string side. This is a one kinematical argument, but there are others. Okay? And this is without going too far. Mm-hmm. Yeah?
How do you motivate this Lagrangian? Because in a normal sigma model, you would just put A, right? So you would construct the two Lagrangians and
Yes.
use this Lagrangian.
Yes. Motivation is on my next slide. Motivation comes with the next slide. Symmetries which this theory has motivate that what we deal with must be Lagrangian for strings on ADS5 cross S5. Yes, indeed. If you just would construct a what you would call principal chiral model based on the group SU2,2/4, then you would not do such a construction. You would just take an element A without any grading, without splitting it on the graded component, define A, G minus 1 dg, and put into the action. And that would be what we call principal chiral field based on the group SU2,2/4. But this is not what we want to construct. We want to construct the sigma model on the coset space, where target is a coset space. And this is precisely what causes us to consider these gradients and put this graded component. This sigma model is in the coset space. That's why it is a bit complicated. It's not that straightforward. Now, symmetries. Okay, so probably the most important point to say that this model, indeed the model on the coset space. That means that this model should not depend on the degrees of freedom which we put in the denominator of this coset. And what we put in the denominator of the coset is a group SO4,1 cross SO5. But now we consider fields. Fields depend on sigma and tau. And now the question is that we have an infinite number of degrees of freedom which sits in the denominator of the coset. These are fields constituting degrees of freedom of SO4,1 cross SO5, and they depend on sigma and tau. And our model, somehow, our Lagrangian, should not depend on them, because we would like to describe the coset. The fact that nothing depends on this subgroup can be seen as follows. There is a local, this Lagrangian exhibits local SO4,1 cross SO5 symmetry. How you can see that? If you take a group element G and multiply it from the right by element from SO4,1 cross SO5, then according to the definition of what this A is, so A is essentially given by G minus 1 dg. And now we substitute here and here G to be equal as G multiplied by some element from the right. And this element is local, so differential dx of it. So when you open this up, you will get that this G minus 1 dg form transforms in the following way. It rotates and it shifts. So what you see there is precisely the form of the gauge transformation, right? Non-abelian gauge transformation. So A transforms as a non-abelian gauge field. But if you now take this guy B to be from SO4,1 cross SO5, and you look precisely at this gradient here, you can see that what is in this gradient component 0, what sits in this here, and this element is precisely the element gradient on 0 component, component with gradient 0, is a component which projects the general matrix A on its SO4,1 cross SO5 path. So A0 is precisely SO4,1 cross SO5 path of the matrix G. Okay? Therefore, from here, you see that if you split this general transformation law for A into the graded components, then the graded components 1, 2, 3 will transform homogeneously, while A0 component is transformed not homogeneously. It has this shift. But looking at the Lagrangian, you see that the component A0 is not there. This component, which is related to denominator of the coset, does not appear in this section. And these components transform homogeneously, transform just by similarity transformation, and similarity transformation decouples under the trace, under the supertrace. And therefore, the action remains to be invariant with respect to the local transformations from the denominator of the coset. So these degrees of freedom play no role. The action does not see them. The action does not depend on them. This is good. This is what we wanted. We wanted to construct the coset action. The second thing is that, is that what you mentioned. Symmetry, what you asked me about is a symmetry. So global symmetry, PSU 2,2/4. And this symmetry acts on the group element by multiplication from the left. And what you do is the following. You take the representative G, say, from coset representative, which sits in the coset. Then you multiply from the left by the element G. Generically, you get out of the coset. Multiplication by arbitrary element of G gets you out of the coset. But then you refactorize your element by a new element from the coset, G prime, and something which belongs to this SO4, 1 cross SO5, which you don't care about because your Lagrangian is invariant with respect to this local symmetry. So basically, G goes to G prime is a global symmetry. So the action is invariant with respect to this global symmetry, the same as the symmetry of the background. This action, of course, also invariant with respect to diffeomorphisms, two-dimensional diffeomorphisms, as usual diffeomorphic invariant string theory should be. This gives rise to the Virasoro constraints, just like in the usual flat space. Components of the stress, two-dimensional stress energy tensor must vanish, and these are components of the two-dimensional stress energy tensor. They give rise you, this gives you Virasoro constraints. And finally, something which also explains the importance and presence of this Vis-Zumina term is that with the Vis-Zumina term, this action has the new local fermionic symmetry called kappa symmetry, which is also there for the string in a flat space, Green-Schwarz string in the flat space. I'm not sure that in the usual courses on string theory you come to the discussion what is called Green-Schwarz superstring. Basically, you discuss the strings with an explicit world sheet supersymmetry. They are called Ramon-Neveu-Schwarz strings, right? That's what you usually do when you come to the discussion of superstrings. And Green-Schwarz superstring people usually postpone to the variant of the course, and typically they never come to it. But this appears to be a very important construction because this is what we use in order to describe string theory in areas 5 cross S5. Ramon-Neveu-Schwarz formulation for such string theory is unknown. We don't know how to couple string world sheet to Ramon-Ramon fields. This is a general problem which people do not know how to solve. That's why they rely only on another known construction known as a Green-Schwarz superstring with an explicit target space supersymmetry. And this is explicit target space supersymmetry in our case is the one which is generated by the group PSU 2,2/4. The presence of this kappa symmetry allows you to remove half of the fermionic degrees of freedom. This is a local symmetry which basically allows you to gauge the way half of the fermionic degrees of freedom. Good, so let me see, maybe last transparency, and then if there are questions, I will answer. So equations of motion are straightforwardly derived from this section. They are given in terms of this two-dimensional vector lambda, again constructed via these graded components that you see how equation of motion look like. And if you conjugate this lambda alpha with the help of the element G, then you see that equations of motion simply are equations of local conservation law. D alpha G alpha is equal to 0. It's a local conservation law. So current J alpha is conserved. Its divergence, which you see there, is equal to 0. And this conserved current is nothing else as a Noether current from the point of view of two-dimensional quantum field theory, or classical field theory if you wish. This Noether current is the one which corresponds to the global PSU 2,2/4 symmetry. So we have two-dimensional theory now, theory on the world sheet. It has PSU 2,2/4 global symmetry, and therefore there should be conserved Noether current. And this is one is there. This is J alpha. And its conservation is due to equations of motion. Okay, I think at this point I probably stop. And the plan for tomorrow is to finish a little bit, to proceed with this, to tell you in which sense this model is integrable, namely Lux representation, and then I go to discuss certain interesting and explicit string solutions. I show you how strings move in this ADS5 cross S5 space, and in particular I will discuss this Gapsa-Klebanov-Polakov string which you asked me about to tell you. Okay, your questions? Yeah.
Any questions?
Yeah, one quick question.
Sure.
You said that this duality between n equals 1 to the means that strings in ADS5 for the 5 is about conformal scaling dimension and spectrum of the strings.
No, it goes beyond that. So in principle, people say, say a conjecture says that these are two completely equivalent theories.
Okay.
And so you have other observables. So spectrum, it's one thing. But for instance, there are correlation functions, say 3-point functions. Wilson loops, non-local observables, they also should match. And this is the whole activity now is going in these directions. What about other observables? Scattering amplitudes, correlation functions, Wilson loops, how all this works? What is the match between these quantities? Sure, the conjecture is about that these theories are equivalent, and they are, in the original conjecture, they are equivalent even beyond large n limit. They are supposed to be equivalent even for finite n. At least this is what conjecture says.
So the status has been checked for some amplitudes?
Yes, amplitudes constitute a very important verification point where you can also, yes, make a progress in matching the quantities on both sides. Scattering amplitudes, Wilson loops. In other words, Wilson loop on the gauge theory has a holographic interpretation from the point of view of strings theory as something which is minimal surface embedded in the ADS space for span by string. Yeah, so this dictionary is extended. I'm representing only a corner of this dictionary, part of it. Certainly.
The spin chain picture in the gauge theory, it only holds in the planar limit.
It holds in a planar limit. Beyond planar limit, you cannot stay with one spin chain anymore. You have to have something which you would call ensemble of spin chains of different lengths, because basically you have double trace operators starting to participate, and you need now to kind of have a multi-spin chain Hilbert space, where in order to be able to incorporate multi-trace operators, it becomes quite complicated. This is not worked out in a way I can easily present or tell you something about it. It's under development. People think about it. Yes?
I think it's a good point to stop. So let's thank Gleb again.